In the space that used to house one transistor, we can now fit 1 billion. That made it so that a computer the size of an entire room now fits in your pocket. You might say the future is small. As an engineer, I'm inspired by this miniaturization revolution in computers. As a physician, I wonder whether we could use it to reduce the number of lives lost due to one of the fastest growing diseases on Earth, cancer. Now, when I say that, what most people hear me say is that we're working on curing cancer. And we are. But it turns out that there's an incredible opportunity to save lives through the early detection and prevention of cancer. Worldwide, over 2/3 of deaths due to cancer are fully preventable using methods that we already have in hand today. Things like vaccination, timely screening, and of course, stopping smoking. But even with the best tools and technologies that we have today, some tumors can't be detected until 10 years until after they've started growing, when they are 50 million cancer cells strong. What if we had better technologies to detect some of these more deadly cancers sooner, when they could be removed, when they were just getting started? Let me tell you about how miniaturization might get us there. This is a microscope in a typical lab that a pathologist would use for looking at a tissue specimen like a biopsy or a pap smear. This $7,000 microscope would be used by somebody with years of specialized training to spot cancer cells. This is an image from a colleague of mine at Rice University, Rebecca Richards-Cordham. What she and her team have done is miniaturize that whole microscope into this $10 part, and it fits on the end of an optical fiber. Now, what that means is instead of taking a sample from a patient and sending it to the microscope, you can bring the microscope to the patient. And then, instead of requiring a specialist to look at the images, you can train the computer to score normal versus cancerous cells. Now, this is important because what they found working in rural communities is that even when they have a mobile screening van that can go out into the community and perform exams and collect samples and send them to the central hospital for analysis, that days later, women get a call with an abnormal test result and they're asked to come in. Fully half of them don't turn up because they can't afford the trip. Now, with the integrated microscope and computer analysis, Rebecca and her colleagues have been able to create a van that has both a diagnostic setup and a treatment setup. And what that means is that they can do a diagnosis and perform therapy on the spot, so no one is lost to follow-up. That's just one example of how miniaturization can save lives. Now, as engineers, we think of this as straight-up miniaturization. You took a big thing and you made it little. But what I told you before about computers was that they transformed our lives when they became small enough for us to take them everywhere. So what is the transformational equivalent like that in medicine? Well, what if you had a detector that was so small that it could circulate in your body, find the tumor all by itself, and send a signal to the outside world? It sounds a little bit like science fiction, but actually, nanotechnology allows us to do just that. Nanotechnology allows us to shrink the parts that make up the detector from the width of a human hair, which is 100 microns, to 1,000 times smaller, which is 100 nanometers. And that has profound implications. It turns out that materials actually change their properties at the nanoscale. You take a common material like gold, and you grind it into dust, into gold nanoparticles, and it changes from looking gold to looking red. If you take a more exotic material, like cadmium selenide, forms a big black crystal. If you make nanocrystals out of this material and you put it in a liquid and you shine light on it, they glow. And they glow blue, green, yellow, orange, red, depending only on their size. It's wild. Can you imagine an object like that in the macro world? It would be like all the denim jeans in your closet are all made of cotton, but they are different colors depending only on their size. So as a physician, What's just as interesting to me is that it's not just the color of materials that changes at the nanoscale. The way they travel in your body also changes. And this is the kind of observation that we're going to use to make a better cancer detector. So let me show you what I mean. This is a blood vessel in the body. Surrounding the blood vessel is a tumor. We're going to inject nanoparticles into the blood vessel and watch how they travel from the bloodstream into the tumor. Now, it turns out that the blood vessels of many tumors are leaky, and so that nanoparticles can leak out from the bloodstream into the tumor. Whether they leak out depends on their size. So in this image, the smaller 100 nanometer blue nanoparticles are leaking out, and the larger 500 nanometer red nanoparticles are stuck in the bloodstream. So that means, as an engineer, depending on how big or small I make a material, I can change where it goes in your body. In my lab, we recently made a cancer nanodetector that is so small that it could travel into the tumor and look for tumors. We designed it to listen for tumor invasion, the orchestra of chemical signals that tumors need to make to spread. For a tumor to break out of the tissue that it's born in, it has to make chemicals called enzymes to chew through the scaffolding of tissues. We designed these nanoparticles to be activated by these enzymes. One enzyme can activate 1,000 of these chemical reactions in an hour. Now, in engineering, we call that 1 to 1,000 ratio a form of amplification, and it makes something ultra-sensitive. So we've made an ultra-sensitive cancer detector. Okay, but how do I get this activated signal to the outside world where I can act on it? For this, we're going to use one more piece of nanoscale biology, and that has to do with the kidney. So the kidney is a filter. Its job is to filter out the blood and put wastes into the urine. It turns out that what the kidney filters is also dependent on size. So in this image, what you can see is that everything smaller than 5 nanometers is going from the blood, through the kidney, into the urine, and everything else that's bigger is retained. Okay, so if I make a 100 nanometer cancer detector, I inject it in the bloodstream, it can leak into the tumor where it's activated by tumor enzymes to release a small signal that is small enough to be filtered out of the kidney and put into the urine. I have a signal in the outside world that I can detect. Okay, but there's one more problem. This is a tiny little signal, so how do I detect it? Well, the signal is just a molecule. There are molecules that we designed as engineers. They're completely synthetic, and we can design them so that they are compatible with our tool of choice. If we want to use a really sensitive, fancy instrument called a mass spectrometer, then we make a molecule with a unique mass. Or maybe we want to make something that's more inexpensive and portable. Then we make molecules that we can trap on paper, like a pregnancy test. In fact, there's a whole world of paper tests that are becoming available in a field called paper diagnostics. All right, where are we going with this? What I'm going to tell you next, as a lifelong researcher, represents a dream of mine. I can't say that it's a promise. It's a dream. But I think we all have to have dreams to keep us pushing forward, even, and maybe especially, cancer researchers. I'm going to tell you what I hope will happen with my technology, that my team and I will we'll put our heart and souls into making a reality. Okay, here goes. I dream that one day, instead of going into an expensive screening facility to get a colonoscopy or a mammogram or a pap smear, that you could get a shot, wait an hour, and do a urine test on a paper strip. I imagine that this could even happen without the need for steady electricity or a medical professional in the room. Maybe they could be far away and connected only by the image on a smartphone. Now, I know this sounds like a dream, but in the lab, we already have this working in mice, where it works better than existing methods for the detection of lung, colon, and ovarian cancer. And I hope that what this means is that one day we can detect tumors in patients sooner than 10 years after they've started growing, in all walks of life, all around the globe, and that this would lead to earlier treatment and that we could save more lives than we can today with early detection. Thank you.